In 2.6, we're going to be combining functions in using different operations like addition, subtraction, and so on. And we're going to be making these new functions. So let's look at some operations that we can do with functions. Well, we could add functions, f of x plus g of x, and create a new function called f plus g of x. Now when we add functions, remember we have to figure out with this new function what its domain is going to be. And since it's made up of f and g, the domain has to be x's that work for both f and g. And I use DOM, short for domain. So the domain of our new function f plus g is simply the domain of f intersected with the domain of g. So it's the x values that f and g have in common. Another way that we can combine functions is through subtraction. So we can create this new function f minus g of x, which is simply f of x minus g of x. And again, domain of f minus g is simply the intersection of the domain of f with the domain of g. We can multiply functions. We can create a new function f times g, which is simply f of x times g of x. And again, the domain of f times g is simply domain of f intersect domain of g. So whatever x values they have in common. We do have to be careful whenever we do a division of two functions, because we could end up with a denominator that's 0. So in that case, we're still going to let the domain of f divided by g be the intersection of the domain of f with the domain of g, but we have to take out x values that make the denominator equal to 0. Let's use these properties. In example 1, we have this function f, which is the square root of 4 minus x, and g is equal to negative 2x plus 5. We want to perform the given operation. So the first one is f plus g of 4. All I have to do is use what's in that box above to split this up into f of 4 plus g of 4. And then I would evaluate these separately. If you look at your function f, it's the square root of 4 minus x. So if I put in 4 for x, I've got the square root of 4 minus 4, which will turn into 0, plus g is negative 2x plus 5. This would be plus negative 2x is 4 plus 5. Square root becomes 0, so that's just gone. And I end up with negative 8 plus 5, which is simply negative 3. So again, the square root of 4 minus 4 is just the square root of 0, so that's gone. Let's try another one. Let's go to B. This is subtraction, so the order that you subtract does matter. This would be f of negative 5 minus g of negative 5. And now f of negative 5, that's just going to be the square root of 4 minus a negative 5 will turn into a plus 5 minus negative 2, and be careful because we're subtracting, I'm going to put a parenthesis. So negative 2 times negative 5 plus 5. That's a lot of negatives. So inside the parentheses, that's just going to be 10 plus 5, or 15. And underneath the square root of 9 becomes 3. And then this will just be 3 minus 15, or negative 12. And again. So this time we're changing the order of our subtraction. We're going to look at g of negative 5 minus f of negative 5. And we did figure out what g of negative 5 was previously, as well as f of negative 5. But I'll compute it over again. It's going to be negative 2 times negative 5 plus 5. That was our g. And we're going to subtract our f with the negative 5. So that would be the square root of 4 minus a negative 5 becomes a plus 5. Well, I guess I didn't need the parentheses. This becomes 15 minus the square root of 9 is 3, so minus 3, and that's a positive 12. In part D, we have f times g of 4, which would be equal to f of 4 times g of 4. And f of 4 is 0, because you'll get the square root of 4 minus 4, which is 0. And we're going to times it by, I actually don't care, because the square root of 0 is just 0. 0 times anything is 0. My answer is going to be 0, but I'll write it out. Pretend like I'm on autopilot. G of 4 is going to be negative 2 times 4 plus 5, which would be 0 times 8. Negative 8 plus 5 would be a negative 3. And then 0 times negative 3 is simply 0. Two more. F divided by g of 3, that's going to be equal to f of 3 over g of 3. And f of 3 is the square root of 4 minus 3, which would turn into the square root of 1, which is simply 1. And g of 3 would be negative 2 times 3 plus 5. We have 1 over negative 6 plus 5 is negative 1, so I wouldn't leave the answer that way. Simplify to negative 1. Last one before we move on, g divided by f, so order matters. That would be equal to g of 4 divided by f of 4. And g of 4 is negative 2 times 4 plus 5. F is the square root of 4 minus 4. So unfortunately, we're going to get a 0 in the denominator. We're going to have negative 8 plus 5 in the numerator, which would give us negative 3. But we have 0. So that just means it's undefined. Or you can write DNE for does not exist. So what happens if you have a function, but you don't have the equation for the function, you just have the graph, like we do in this graph here. So we're going to use the graph to evaluate each of these expressions. The first expression is f plus g of 3. So remember, that's just simply f of 3 plus g of 3. And this 3, remember that this is an x value. If we look on the graph and we look at our function f, remember we're going to start at 3 for our x, and it's going to correspond to some point on our graph f of x. So f of 3 would just be the y value that goes with an x value of 3, which in our case would be 2. So f of 3 is 2, plus, if you look at the function g, the y value would be 1. And I have 3. G minus f of 0, that would be g of 0 minus f of 0. If we look at the graph, we're looking at where x is equal to 0. And then we go to g. G of 0 has a y value of negative 2 minus f of 0 has a y value of 1. So it's going to be negative 2 minus 1, which would be a negative 3. Now f times g of 3, that would be f of 3 times g of 3. So again, we're going to an x value of 3. That corresponds to an f of 3 or y value of 2. So this would be 2 times g of 3 is 1. So 2 times 1, I'm going to put parenthesis, which is just 2. And f of 0 over g of 0, so we go where x is equal to 0. F of 0, that's a y value of 1. G of 0, that's a y value of negative 2. So it's negative 1/2. And then the last would be f of negative 1 plus g of negative 1. So we're going to an x value of negative 1, and we go to our graph f, and the y value there is 0, plus, if we go to negative 1, notice that there's no graph for g. It does not exist. I'm just going to put dne. And now you can see why when you combine functions, you're going to take the intersection of the domains, because whatever x you put into your function, in this case our function is f plus g, so whatever x I put into f plus g has to work with both the function f and the function g. So even if I have a 0 for the f of x, because I have does not exist for the g of x, then f plus g of negative 1 does not exist. So this whole thing does not exist. Okay, so now let's move on to, instead of putting values into our new functions, we're just going to make new functions and just leave our variable x in play. Example 3, we have our function f of x and g of x, and we need to find f plus g, f minus g, f times g, and f divided by g, and their domains. Well, let's look at f plus g of x. Okay, so remember, that's simply f of x plus g of x. And I know what f of x is. It's 3x minus 2. Plus, I know what g of x is. It's 5x plus 9. So when I combine my like terms, I have 8x plus 7. That's my new function, f plus g of x. Maybe I'll rewrite this so you could see our new function. Well, what is its domain? The domain is the intersection of the domain of f and the with the domain of g. So what is the domain of f? If you look at f of x equal to 3x minus 2, if you replace the f of x with a y value, you could see that y equal to 3x minus 2 is simply a line. It's a line in slope-intercept form. If you were to graph it, you would see that the domain goes from negative to positive infinity. So I could see that the domain of my function f is negative infinity to positive infinity. And the same thing for g of x. If you replace g of x with y, you have y equal to 5x plus 9, which is a line, and it has the same domain. Negative infinity to positive infinity. Which means that the intersection, the domain of f, and that's what we're looking for. Oops. Intersect, not equal. Intersect with the domain of g. That's just what they have in common, but they're both negative to positive infinity, so the intersection is also negative to positive infinity. And that would be the domain of f plus g. So going back to the very first page, whenever you add two functions, you're taking the intersection of their domains. Now, if we find f minus g, it's the same domain. It's the intersection of the domain of f with the domain of g, and also f times g. So before I even figure out what those functions are, I already know what their domains are. the domain of f minus g is also negative to positive infinity. And the domain of f times g is also negative to positive infinity. We do have to be careful with the division because we have to take away values and make the denominator 0, if there are any. Well, let's go ahead and figure out what f minus g is. F minus g of x is equal to f of x minus g of x. And f of x is 3x minus 2 minus, don't forget we're going to distribute the negative over the g of x, which is 5x plus 9. To get 3x minus 2 minus 5x minus 9. So negative 2x minus 11. And that would be my new function, f minus g of x. And we've already got the domain. What about f times g of x? Again, it's just f of x times g of x. But this time we're multiplying binomials. So in parentheses, you would have the 3x minus 2, parentheses 5x, 5x plus 9. And then if you FOIL or multiply that out, 3x times 5x should be 15x squared, and then negative 2 times positive 9, 3x, well, maybe I'll do the 27x first. I have a certain order that I like to do these in. I think that's it. So the 27x minus 10x would be a positive 17x. So it looks like f of g of x is equal to 15x squared plus 17x minus 18. And again, the domain is simply the intersection of domain f, domain g, which is negative to positive infinity. Now the last one, which would be the division, f divided by g of x. That's going to be f of x divided by g of x. And here our f of x is simply 3x minus 2. G of x is 5x plus 9. Notice that there's nothing to factor out or reduce. So this is f over g of x. So that wasn't bad. But what about the domain? So remember, the domain is going to be equal to the domain of f intersect with the domain of g. But we have to take away where g of x is equal to 0. So g of x cannot be equal to 0. So we already know that the domain of f intersect the domain of g is negative to positive infinity. But look at the denominator. It's 5x plus 9. This is going to be equal to 0 when x is equal to negative 9 over 5. So x cannot be equal to negative 9 over 5. So now the domain of our new function f divided by g is going to be negative infinity to negative 9 over 5 with parentheses because we can't use it, union negative 9 over 5 to positive infinity. That's probably the most difficult domain, is the f divided by g, because you have to figure out where the denominator is 0. In this next example, we're going to discuss what we call the difference quotient. Now, the difference quotient is another way to write the slope, even though it doesn't look like that. And in calculus, we look at the difference quotient and we look at what happens as h in the denominator, as this h gets really, really small, like very close to 0. And in calculus, that's called our derivative. And the derivative is most of calculus. So this difference quotient is most of calculus. We're going to go ahead and compute the difference quotient given these two functions. So in part A, we have f of x equal to 3x minus 1. Now, if I compute the difference quotient, all I have to do is substitute in for this formula, which is f of x plus h minus f of x over h. Now the h stays, nothing I can do with that. I don't have to worry about f of x either because it's given to me. I know that f of x is equal to 3x minus 1, so I can substitute 3x minus 1 for the f of x. The question is, what is this f of x plus h? Well, remember, you have a function. The function is f of whatever is going to equal to 3 times whatever I put in minus 1. So if you simply put in x plus h wherever you see x, that is what x plus h is. So f of x plus h, if I were to distribute the 3, would be 3x plus 3h minus 1. And now when I compute f of x plus h minus f of x over h, I have all the pieces I need. F of x plus h is simply 3x plus 3h minus 1 minus my f of x is 3x minus 1. Don't forget you're going to distribute the negative. All of this is over h. So 3x plus 3h minus 1 minus 3x plus 1 over h. When you're simplifying these difference quotients, if nothing cancels, then you did it wrong. Something always cancels. So notice here I have a 3x minus 3x, so that's 0. Minus 1 plus 1, that cancels. And this is simply 3h over h. And now the h's cancel. I have 3. So recall I said this was another way to write the slope formula. And if we go back to our function, our f of x, and I'm just going to replace f of x with y. It's y equal to 3x minus 1. This is the equation of a line with slope of 3 because it's in slope-intercept form. So if you use the difference quotient and your function is a line, what you get back is the slope. Well, what happens if the function's not a line? In part B, g of x is equal to x squared plus 1. That's the squaring function. It's not a line. It curves. Well, we could still use this difference quotient function to figure out what it would be if we use g of x equal to x squared plus 1. So remember, we have the g of x. We need the g of x plus h. So it's just a variable. Whether we use f or g, it's the same difference quotient. So in this case, it would be g of x plus h minus g of x over h. I have g of x, I have h. What is our g of x plus h? I like blue better. So that just says wherever you see x, you're going to replace it with x plus h. So we're going to square that. And the plus 1 is on the outside, right? We're not putting the x squared plus 1 into g of x plus h. We're putting g of x plus h into... We're putting the x plus h in for the x in g of x. Okay, so don't just distribute that 2. It's not x squared plus h squared. Remember, this is x plus h times x plus h. And if you did FOIL or multiply that all out, you should get x squared plus xh plus xh would turn into a 2xh plus h squared plus 1. So g of x plus h is equal to x squared plus 2xh plus h squared plus 1. Now I'm going to finally compute g of x plus h minus g of x over h. So the g of x plus h, that would be our x squared plus 2xh plus h squared plus 1 minus g of x was x squared plus 1 all over h. X squared plus 2xh plus h squared plus 1 minus x squared minus 1 all over h. So what cancels? X squared minus x squared. 1 minus 1. Notice that when we've been canceling, what has remained is everything that has an h in it. This would be 2xh plus h squared over h. Now think about factoring out an h. You have 2x plus h over h. And the h's cancel, which leaves me with 2x plus h. Let me just rewrite that. Okay, so that's enough with the difference quotient. Don't make it harder than it is. It's simply a substitution. The last thing we're going to talk about is another way that we can combine functions. So here we have what's called a composite function. And we've got this weird circle between the f and the g. And that's not the degree symbol. That's not a multiplication. That literally means of. So this reads f of g. So this is a composite function, sometimes called a composition of functions. And a composition or a composite function just says you're going to take one function and you're going to put it inside the other function. So how you do that is you look at which function is closest to the variable. In this case, we're using x. That one goes on the inside. And then the other function goes on the outside. So it's a substitution where you put one function, in this case it's g of x. I'm putting g of x inside f of x. Now when I create this new function, f of g, it's going to have a domain, and the domain's a little bit, could be a little bit confusing here, a lot of notation. So the domain of f of g is going to be all x that are in the domain of g, such that g of x is in the domain of f. So that's a little bit confusing to understand. Let's draw ourselves a picture of what's going on. So let's say that I have the domain of g. So it's going to have some x value. G is going to take that x value, it's going to do whatever it's defined to do, and it's going to spit back a y value in its range. Instead of y, remember g of x is equal to y, so I'm just going to write g of x instead of y. So g takes x from its domain, and it gives us back a y or a g of x in the range. But now I'm putting this inside of my function f. So f is now going to take these values and give us back a y value from the range of f. So these y values, I'm just going to call them f of x. Now since we're putting these g of x, these y values into f, whenever you put something into a function, that's its domain. So now this range of g That's going to be our domain of f. So what the definition says for the domain of f of g is that you're going to take all the x's in the domain of g such that those g of x's are in the domain of f. So we're not going to be computing the domain of composite functions in this lecture, and in Math 135 at Windward you're actually not responsible for finding the domain of composite functions. However, you may run across one or two MyLab assignments that may have it, so just go ahead and follow that definition if you could. And so example 5, we have f of x square root of 2x minus 1 and g of x is x squared plus 5. And we want to evaluate the following. We're going to do f of g of 0. Now remember, the function closest to what you're putting inside, in this case our x is 0. That's going to go inside of f is on the outside. So f is on the outside. G of 0 is on the inside. So we have to first figure out what g of 0 is, so you're working from the inside out. So if we put in 0 for x, g of x is x squared plus 5. This just becomes 5. And now this f of, we replace g of 0 with 5. So we're putting 5 in for x in our function f now. And that is the square root of 2x minus 1. So this will be 10 minus 1. Square root of 9 is simply 3. Let's go to b. We switched the order around, but remember, you're just looking at which function is nearest to your variable x. And in this case, x is 3. And that's what you're going to do first. That's what goes inside of g is on the outside. So we do f of 3 first, and f of 3 is going to be the square root of 3 times 2 is 6 minus 1. So the square root of 5. We're going to put the square root of 5 into our function g. So the function g is x squared plus 5, which means we're going to square root of 5 and then add 5 to it, which becomes 5 plus 5, or 10. So again, just a substitution. Now here's my second b. I did not relabel. So when we compose functions, it doesn't have to be with a different function. It can be a function composed with itself. In this case, f is closest to 2, so I want to do that first, and then once I figure out what that is, I'm going to put it back into f. So this is f of 2. Now f of 2 is the square root of 2 times 2, so 4 minus 1, be the square root of 3. This becomes f of square root of 3. Now this is going to look a little weird, but it is what it is. We're putting in the square root of 3 in for x. So you get the square root of 2 times the square root of 3 minus 1. And we could put this in a calculator and find a decimal approximation, but really this is it. Without a calculator, this would be an exact solution. Let's look at c. This time we're composing g with itself. So we're going to do g of negative 1 first. Whatever that is, we're going to put it back into g. So this is g of negative 1. So what is g of negative 1? So we're going to take negative 1, we're going to square it, and then add it to 5. So that would be 6. So I have g of 6. And now when I square 6, I get 36 plus 5. It looks like this is going to be 41. So we don't have to put in a value into these composite functions. We can just create a composite function with just a variable x. So if I was going to define this new function f of g of x, remember the g of x goes first. It goes inside my function f. I would have f of whatever g of x is. But I know what g of x is. It's defined as x squared plus 5. So this is f of x squared plus 5. So that tells me in my function f, wherever I see x, I'm going to put in x squared plus 5. So I'm going to write this one out so it's clear. This is 2x. But instead of x, I have x squared plus 5. And then it's a minus 1. This is what I need to simplify. Becomes the square root of 2x squared plus 10 minus 1, which is going to be 2x squared plus 9. And that's as far as I can go. So this is my new function f of g. Well, what does it look like if we change the order around? And this is our last example. Remember, this says we're going to do f of x first and then put that into g. So this becomes g of whatever f of x is. And in this case, our f of x is the square root of 2x minus 1. Remember, g of x is x squared plus 5. So when I put 2x minus 1, square root of 2x minus 1, into g of x, for x, I'm squaring it, and I'm adding 5. So here the square root and the square is going to cancel. I'll end up with 2x minus 1 plus 5, which is simply 2x plus 4. And that would be my g of f. And that is it.